Hello everyone, we will now present our demo titled Membership Inference Test and its application to face recognition models. In June 2023, the European Parliament imposed an obligation on developers of AI models to protect the fundamental rights of citizens. This was accompanied by regulations such as the requirement to register AI models in a European database with access to the models. This necessitates new auditing tools to ensure compliance with the relevant legislation. Creating these tools is a fundamental step in the development and evolution of artificial intelligence, thus requiring a concerted effort from the scientific community in this direction. Currently, developers can hide behind the model's weights to use data they do not have access to, and this is where our work comes into play. The data used in training leaves a trace in the weights. Is this trace detectable? To investigate this, we leverage knowledge extracted from the AI model and apply it in our membership inference test to attempt detection. If we manage to detect the data used in training, we will remove the veil behind which developers hide and thereby achieve a more transparent AI. This is a significant step in the development of tools that safeguard the rights of citizens and provide us with greater reliability. Next, we will present the entire workflow of the system. We have the data D, with which the audited model has been trained, and external data epsilon, that the audited model has not been trained on. The process involves inputting the data D and epsilon into the audited model and extracting activation information from intermediate layers of this audited model. This activation information is what we refer to as auxiliary auditable data. Depending on the layer I from which you obtain this information, you will get different data. This auxiliary auditable data and the model outcome are used as input in our MINT model. In this work, we have included the entire workflow. However, based on developer preferences, it can start directly from the auxiliary auditable data or / and the model outcome provided to us. This data is used to train the MINT model, which learns to differentiate between data used for training and data not used for training. In this work, we will focus on a facial recognition model as the audited model. Two different architectures have been used for the MINT model, each handling information differently and consequently yielding different results. In this first case, we will explain the vanilla MINT model. The auxiliary auditable data obtained from the network consists of activation maps from the output of a convolutional layer in the facial recognition model. The model outcome in this case is the output embedding of the model. For this vanilla MINT model, we take the maximum from each activation map of size hxw. If there are C filters in that convolutional layer, we have C activation maps, and obtaining the maximum from each map results in a vector of size C. This vector is used for the vanilla MINT model, which is therefore a multi-layer perceptron. Additionally, the output embedding can be used as input for this vanilla MINT model. For more technical details and a more in-depth explanation, please refer to the full paper. Next, we have the CNN MINT model. This approach handles the information from activation maps differently. Instead of selecting the maximum from each activation map, we analyze the set of activation maps using a CNN. This way, we provide the network with all the available information to seek the patterns it deems best for detection. Again, for a more in-depth understanding of the technical details and implementation, please refer to the full paper. Before proceeding with the platform presentation, we will showcase the classification results of our MINT model. In this work, we used a facial recognition model from the well-known Insight Face project as the audited model. Specifically, we employed a ResNet 50 model trained on the MS1 MV3 database and a cost face loss function. At the top of the table, we have the architecture of the MINT model used. On the left, we have the information used as input in our MINT model. The layer row indicates the layer from which activation maps were obtained. The lower the number, the closer the activation maps are to the input of the audited model, which in this case is our facial recognition model. The model outcome is the output embedding of the network. The All CONV Layers column indicates that it is the concatenation of all the information from the activation maps. Let's first explain the NA values in the CONV model column. As we have explained, the CONV MINT model analyzes activation maps through a convolutional architecture, and therefore using the output embedding makes no sense as it consists only of a vector. Regarding the concatenation of activation maps from convolutional layers, it is important to note that they have different resolutions, meaning H and W are of different sizes for different convolutional layers, and therefore concatenation is not possible. For the vanilla model, as these data are vectors, this concatenation is straightforward. The values in the table represent the detection accuracy on the evaluation set. As we can see, the highest accuracy is achieved with the CONV MINT model using the activation maps from the convolutional layer closest to the input of the audited model, reaching 89%. The closer the activation maps are to the output, the worse the performance of the CONV MINT model. For the vanilla model, the results are lower. In this case, we have the advantage of being able to concatenate the outputs of the convolutional layers, and this approach yields the best results with an 84% accuracy. Once again, the next best results are obtained with the activation maps closest to the input of the audited model. However, in this case, the information closer to the output achieves the next best results. For more specific details about the evaluation of these models, or further results and analysis, please refer to the full paper. We present a web platform, where citizens can upload any picture and receive a report indicating the probabilities that this image was used to train an AI model. The initial version of the platform contains a limited number of models, and it was developed as an academic exercise to promote transparency in artificial intelligence. In the future, the number of AI models will depend on the collaboration between academia, industry, and governmental agencies. I briefly present the results of this initial version. First, we upload an external photo not present in the D database used for training the model. Next, the system processes the image and provides us with the probability of belonging to each of the models for which we have created a MINT model. In this case, the external image yields low probabilities of belonging to the training set. Now, let's consider the opposite scenario, where the image does belong to the D dataset. In this case, the system processes the image and provides high probabilities of belonging to the dataset of the models being tested. The ultimate goal of this platform is to encompass the maximum number of models, not only for facial recognition but for any type of model, in order to test AI models and detect whether they have been trained on unauthorized data. This will contribute to achieving a more transparent and fair AI. Our tool enables the detection of when data has been used in the training of a network, with a promising percentage. We present a web platform where, with the collaboration of academia, industry, and governmental agencies, a more transparent AI can be achieved.